Have you ever looked up at the night sky and wondered what secrets it holds? Beyond the twinkling stars and familiar constellations lie some of the universe's most mind-bending phenomena. Today, we read diving deep into one of the most mysterious and captivating of them all, the black hole. At first glance, a black hole sounds like something straight out of a science fiction movie. But it's very real, a product of physics pushed to its absolute limits. Imagine a place in space where gravity is so powerful that nothing, not even light, can escape. That's what makes a black hole black and completely invisible. It's not a hole in the traditional sense, but an object where matter has been squashed into an impossibly small space, creating something with truly unbelievable properties. Black holes aren't just cosmic vacuum cleaners, though. They are nature's ultimate laboratories. They give scientists a unique chance to see how gravity works in extreme conditions, where our everyday understanding of physics completely breaks down. This is where Einstein's general theory of relativity truly shines. By studying black holes, we can witness the fabric of space and time being warped and twisted. We see light bending in impossible ways and matter behaving in ways that defy our intuition. They are a window into a part of the universe that challenges everything we think we know. So what exactly is a black hole made of? It's an object of unimaginable density and mass, something far beyond anything we can experience on Earth. All the material that once made up a massive star, or even multiple stars, gets crushed down to a single point. At this point, gravity becomes the undisputed king, a force so strong that nothing can stand against it. Even light, the fastest thing in the universe, gets trapped in its gravitational grip, making the black hole a true cosmic enigma. At the very heart of every black hole is a singularity. This is a theoretical point where density becomes infinite, and the laws of physics as we know them cease to exist. Wrapping around this singularity is the event horizon. Think of it as an invisible, one-way door. Once anything crosses this boundary, whether it's a particle, a ray of light, or a whole star, it's trapped forever. To someone watching from the outside, it would look like time itself freezes at this edge, making the event horizon the defining feature of a black hole. Now, you might have heard of neutron stars. They are also superdense objects left over from dead stars, but they are fundamentally different from black holes. A neutron star forms when a massive star explodes in a supernova. Its core collapses, but it's held up by something called neutron degeneracy pressure. This pressure stops the collapse, leaving behind an incredibly dense ball of neutrons, only a few dozen kilometers across. It's massive, but it's stable. A black hole, on the other hand, forms when the collapsing star's core is so massive that even neutron degeneracy pressure can't stop it. Gravity wins the fight, and the collapse continues all the way down to that singularity. An event horizon forms, and the object is sealed off from the rest of the universe. Unlike a neutron star, which has a solid surface, a black hole is pure gravity. This difference really highlights the genius of Einstein's theory of general relativity. It explains how mass curves spacetime, and in a black hole that curvature becomes so extreme that our classical physics just doesn't work anymore. Neutron stars also warp spacetime, but we can still see radiation coming from their surfaces. With black holes, once something crosses the event horizon, it's gone for good. By comparing these two cosmic giants, we see the incredible variety of ways a star's life can end, pushing the boundaries of what we thought was possible. So how is a black hole born? The process is one of the most dramatic events in the entire cosmos. The most common way is from the death of a massive star, one that's several times bigger than our own sun. Throughout a star's life, there is a constant battle between two forces, the outward push from nuclear fusion in its core and the inward pull of its own gravity. When the star runs out of fuel, the fusion stops. The outward pressure disappears, and gravity takes over. The star's core collapses catastrophically under its own immense weight. This implosion can trigger a spectacular supernova explosion, which blasts the star's outer layers into space. This is one of the brightest and most energetic events in the universe. Meanwhile, the incredibly dense core keeps collapsing, eventually forming a singularity. The event horizon forms around it, and a new black hole is born. But not all black holes come from stars. Scientists also think there might be primordial black holes, which could have formed in the chaotic early moments of the universe right after the Big Bang. And then there are the supermassive black holes. These are the titans lurking at the centers of most galaxies, including our own Milky Way. They have masses millions, or even billions, of times that of our sun. We're still not entirely sure how they got so big. but it's less likely they grew over billions of years by merging with other black holes and gobbling up gas, dust, and stars. There's also a hunt for intermediate mass black holes, which would bridge the gap between the stellar-sized ones and the supermassive giants. Finding them is a huge goal for astronomers today. So, from the life cycle of stars to the very beginning of time, black holes are a natural, if extreme, part of our universe. Each one is a laboratory for testing the limits of physics and exploring how matter and energy behave in the most warped regions of space-time. Even though a black hole itself is invisible, the area around it is one of the most dynamic and energetic places you can imagine. This is the living shell of the black hole. Circling the black hole is a structure called an accretion disk. This is a swirling, superheated disk of gas, dust, and stellar debris that's been pulled in by the black hole's gravity. As this matter spirals closer, it speeds up, heats up to millions of degrees, and glows brightly in X-rays and visible light. This accretion disk is how astronomers can find and study black holes. It's the glowing evidence of their immense gravitational pull. But that's not all. Some black holes also produce powerful jets. These are colossal streams of matter that get shot out from the black hole's poles at nearly the speed of light. These jets are formed by the complex interaction of magnetic fields and the matter in the accretion disk. They can travel for millions of light years, stretching far beyond the host galaxy. These jets have a huge impact on their cosmic neighborhood, sometimes triggering star formation in distant clouds of gas and other times blowing that gas away and stopping it. So, while the black hole itself is a silent, invisible point of no return, its surroundings are a spectacular show of extreme physics. The accretion disk and jets create a visible, energetic aura that allows us to witness the black hole's power. It's a place where matter moves at unbelievable speeds. Radiation is incredibly intense, and magnetic fields channel energy across galaxies. A black hole isn't just a point of gravity. It's the engine at the heart of some of the most powerful processes in the universe. Black holes challenge our understanding of space, time, and reality itself. They are a testament to the sheer power and mystery of the cosmos. As we continue to develop new telescopes and new theories, we get closer to unraveling their secrets, one discovery at a time. What will we find next in the shadows of these cosmic giants? Only time will tell. Stellar black holes, or stellar mass black holes, are the aftermath of a dramatic cosmic event, the death of a massive star. Imagine a star many times more massive than our Sun running out of fuel. Its core collapses under its own immense gravity, triggering a spectacular supernova explosion. What's left behind is an object so dense, so compact, that nothing, not even light, can escape its pull. These black holes typically have masses ranging from a few to several tens of times that of our Sun. While they might be small on a cosmic scale, their gravity is anything but. Matter that gets too close is accelerated to incredible speeds, forming a glowing, superheated ring called an accretion disk, which blasts out powerful X-rays. Stellar black holes are scattered throughout galaxies like our own, sometimes wandering alone and other times found in binary systems, locked in a gravitational dance with a companion star. In these cases, the black hole can pull material from its partner, creating what we call an X-ray binary. These bright emissions are how we often detect them. Studying these objects gives us amazing insights into the final stages of massive stars and the violent processes that shape our universe. Now, let's move on to the middleweights of the black hole family, intermediate mass black holes. For a long time, astronomers knew about the small stellar ones and the giant supermassive ones, but there was a huge gap in between. That's where these guys come in. With masses ranging from a few hundred to tens of thousands of solar masses, they are the missing link in black hole evolution. But where do they come from? Unlike their smaller cousins formed from a single star, their origin is still a hot topic of research. One leading theory is that they form in the crowded hearts of dense star clusters, where multiple stellar black holes merge over time. Another idea is that they could be the primordial seeds of galaxies forming in the early universe. Finding them is tricky. They aren't as bright as the giants at galactic centers, and their gravitational influence is more localized. We usually detect them indirectly by observing the strange, speedy movements of stars in clusters or by catching faint X-ray glows from matter falling into them. These intermediate black holes are incredibly important because they might be the stepping stones to creating the supermassive black holes we see today. They show us that the universe builds these extreme objects on many different scales, and their discovery opens up exciting new ways to study how galaxies grow and evolve. And that brings us to the true titans of the cosmos: supermassive black holes. These are the colossal giants that reside at the heart of nearly every large galaxy, including our very own Milky Way. We were talking about objects with masses ranging from millions to billions of times that of our Sun. Their gravity is so immense that it dictates the motion of entire galaxies. They influence the orbits of stars, control the distribution of gas and dust, and can even regulate the birth of new stars in the galactic core. The supermassive black hole at the center of our galaxy, Sagittarius A star, is 4 million times the mass of the Sun. So how do they get so big? They grow over billions of years by feasting on gas, dust, and even entire stars that venture too close. They also grow by merging with other black holes during galactic collisions. When they are actively feeding, they can create some of the brightest objects in the universe, known as active galactic nuclei or quasars. Sometimes they even launch enormous jets of matter from their poles at near the speed of light, which can extend for hundreds of thousands of light years, impacting the entire galactic neighborhood. Studying these giants isn't just about understanding one object. It's about understanding the entire life story of galaxies. They are the anchors of cosmic structure, and their existence reveals the sheer scale and power of the forces that shape our universe. So we've met the different types, but how do black holes actually work? It all comes down to gravity, but on a level that's almost impossible to comprehend. Their immense mass warps the very fabric of space-time around them. This curvature creates a powerful gravitational well that pulls everything in. As matter gets closer, it accelerates to incredible speeds and spirals inward, forming that bright, hot accretion disk. The friction and intense gravitational forces in this disk heat the material to millions of degrees, causing it to emit powerful X-rays and gamma rays. This is why, paradoxically, the region around a black hole can be one of the brightest places in the universe. It's not the black hole itself that shines, but the matter being torn apart just before it crosses the point of no return. One of the most mind-bending effects of a black hole's gravity is something called gravitational lensing. Because a black hole bends space-time so dramatically, it also bends the path of light that passes nearby. Imagine light from a distant star or galaxy traveling towards us. If a black hole sits between us and that distant object, the light's path is warped. From our perspective on Earth, the background object can appear distorted, magnified, or even stretched into arcs and rings, like looking through a cosmic magnifying glass. This not only helps us find and measure the mass of black holes, but also allows us to see galaxies that are so far away they would otherwise be completely invisible. This effect is a stunning visual confirmation of Einstein's theory of general relativity. The experience of anything getting close to a black hole is even more bizarre. The gravitational pull is so much stronger at the part of an object closer to the black hole than at the part farther away. This difference in force creates an extreme stretching effect known as spaghettification. An object, whether it's a star or an unfortunate astronaut, would be stretched out into a long, thin noodle of atoms before being consumed. So while we can never see inside a black hole, the incredible phenomena happening around it, the glowing accretion disks, the powerful jets, the warped light, and the spaghettification of matter turn these dark objects into natural laboratories for extreme physics. They push the boundaries of our understanding and allow us to test the very laws that govern reality. They are not just cosmic destroyers. They are creators of spectacular phenomena and key players in the grand cosmic story. Black holes truly represent the extremes of our universe, from the stellar remnants of dead stars to the supermassive anchors of entire galaxies. They challenge our understanding of space, time, and gravity itself. Every new discovery about them brings us one step closer to unraveling the deepest mysteries of the cosmos. Ever wonder what happens when time itself gets twisted? Imagine a place where a single hour could equal 1,000 years on Earth. Near a black hole, gravity is so intense that it literally slows down time. This isn't science fiction. It's a real effect called time dilation, predicted by Einstein's theory of relativity. If you were to watch someone fall towards a black hole from a safe distance, they would appear to slow down, eventually looking like they're frozen in time right at the edge, never quite crossing the point of no return. But for the person falling in, time would feel completely normal. It is one of the most incredible proofs that gravity doesn't just pull on objects, it shapes the very fabric of space and time. But this cosmic mystery deepens. What happens to the stuff that falls in? Quantum mechanics, the bedrock of modern physics, says that information about any object can't just be destroyed. Yet, a black hole seems to swallow matter and its information whole, crushing it into an infinitely dense point called a singularity. This clash between two fundamental theories creates what's known as the information paradox. Did the information vanish forever, breaking a law of physics? Or is it somehow preserved? The legendary physicist Stephen Hawking proposed that black holes aren't entirely black. They slowly leak energy, known as Hawking radiation, which might carry the lost information back out into the universe. Solving this paradox is one of the biggest challenges in science today, pushing us toward a grand unified theory of everything. Black holes aren't just isolated oddities. They are the architects of the cosmos. At the heart of most large galaxies, including our own Milky Way, lurks a supermassive black hole. These giants act like a galactic pacemaker, their immense gravity orchestrating the dance of stars, gas, and dust. By tracking the orbits of stars whipping around the galactic center, astronomers can measure the mass of this invisible behemoth. It's like feeling the pulse of the galaxy to understand its heart. And what a powerful heart it is. As gas and stars get pulled in, they form a swirling, superheated disk around the black hole called an accretion disk. This disk can become hotter than the core of a star, blazing with X-rays and gamma rays. But that's not all. In a spectacular display of power, some black holes launch colossal jets of matter and energy that blast out from their poles, traveling for hundreds of thousands of light years. These jets can either ignite furious bursts of star formation by compressing gas clouds, or they can blow the gas away, effectively sterilizing the galaxy and shutting down star birth. In this way, supermassive black holes are the ultimate cosmic gardeners, deciding whether a galaxy will be a bustling metropolis of new stars or a quiet dormant system. But it's not just the supermassive ones that shape the universe. Smaller, stellar mass black holes, born from the collapse of giant stars, also play a crucial role. They can stir up star clusters, influence the merging of galaxies, and help build larger cosmic structures over billions of years. When two black holes collide, they unleash one of the most powerful events in the universe: a storm of gravitational waves. These are ripples in spacetime itself, which we can now detect on Earth. This new way of listening to the universe has opened an entirely new window into the cosmos, allowing us to witness events that are completely invisible to traditional telescopes. From the smallest to the largest, black holes are fundamental drivers of cosmic evolution, their gravitational influence shaping the destiny of entire galaxies. So black holes are more than just cosmic vacuum cleaners. They are nature's ultimate laboratories, where the most extreme conditions allow us to probe the deepest secrets of physics. The information paradox is just one puzzle. What about wormholes? Some theories suggest that black holes could be gateways to these hypothetical spacetime tunnels, potentially connecting distant parts of our universe or even linking to other universes entirely. While purely theoretical for now, the idea that a black hole could be a cosmic shortcut is incredibly tantalizing. Then there's the holographic principle. This mind-blowing concept suggests that all the information contained within a three-dimensional volume of space, like the area around a black hole, could be perfectly encoded on its two-dimensional surface, the event horizon. It's like saying our three-dimensional reality might just be a projection, a hologram, generated from a lower dimensional surface. Black holes, in this view, are the key to understanding this fundamental structure of reality itself. It's a concept that sounds like it's straight out of a movie, but it's at the forefront of theoretical physics. Even more bizarre, some theories like string theory predict the existence of microscopic black holes. These tiny objects could have formed in the fiery aftermath of the Big Bang and might still be drifting through the cosmos. Though we can't see them, their presence could be subtly influencing everything from dark matter to the fundamental forces of nature. Studying black holes, both big and small, allows us to test the very limits of our understanding in ways we could never replicate here on Earth. Let's zoom in on some of their most spectacular features. Black holes are not static. They grow. By feeding on surrounding gas, dust, and even entire stars, they increase their mass and expand their event horizon, becoming ever more powerful. At their very center lies the singularity, that point of infinite density where our current laws of physics completely break down. What happens there remains one of the greatest unsolved mysteries in all of science. Many black holes also spin, some at nearly the speed of light. This incredible rotation doesn't just warp space. It drags space-time around with it in a cosmic whirlpool. This effect, known as frame dragging, twists the shape of the accretion disk and helps launch those powerful jets we talked about. This spinning energy can be released in brilliant flashes of X-rays and gamma rays, providing us with stunning evidence of these relativistic phenomena. And as we've seen, when these spinning giants collide, they create gravitational waves. The first detection of these waves in 2015 by the LIGO and Virgo observatories was a Nobel Prize-winning breakthrough. It confirmed another of Einstein's predictions and gave us a brand new sense to perceive the universe. We can now listen to the silent symphony of cosmic collisions, hearing the echoes of black holes merging billions of light-years away. From their influence on time and information to their role as galactic engines and windows into quantum gravity, black holes are where all the deepest mysteries of the universe converge. They are not just cosmic destroyers, but cosmic creators, shaping the universe we see today and offering us a tantalizing glimpse into the true nature of reality itself. They challenge our imagination and drive us to ask the biggest questions. What is space? What is time? And what are the fundamental laws that govern it all? The answers may be waiting for us, hidden in the darkness of a black hole. See you next time.